Let's see. Actually, let me do new stuff, and I'll, are you coming to office hours today? Any chance? Okay. Maybe I'll try to just post a solution to that. Okay, so today let's get back to internal loads. Because I know those take forever. If I do a solution, it'll take the whole class.
Yeah, that's fine.
Okay, so what I had just said at the end of class last time was that, so imagine you have this beam, and it's 500 newtons down at each end, and 1,000 newtons up in the middle. And you can check that that's in static equilibrium. And then I said, let's think about calculating the internal load at 4 different lines. So one here, one here, one here, and one here. Okay, so in all cases, we're gonna isolate the part of the beam from the left up until that line. And what we saw was that, so if we make these cuts at the 4 lines, you know, the 4 red lines, we saw that there were 2 pairs of qualitatively similar free body diagrams. Okay, so there was the one that looked like this, and the one that looked like this. Oh my God, so many people here now. And then there were the 2 other ones, the one that looked like this, and this. Okay, so you know, these 2 are the same, somehow sort of the same. These 2 are sort of somehow the same. You can't draw a single free body diagram that represents every one of these cuts, but you can imagine drawing a free body diagram that represents both of those first 2. And you could imagine drawing a free body diagram that represents each of these last 2, right? The only difference is you can think of like the length, like this distance, as x. And x is just a different value in both of those cases, right? So in this case, X is, how long did I say this thing was? I forgot. 1 meter. Yeah. So like in this case, X is 0.51 meters. In this case, X is 0.99 meters. In this case, X is 0.01 meters. In this case, it's 0.49 meters. But you could imagine drawing a free body diagram that represents both of those first two, and you just have X representing the length, and then the second two have X representing the length, and you could draw that. What you would end up with, what we're going to end up with is for each set of qualitatively similar cuts, we can represent the internal loads as functions of X, okay? And we'll go through how to do that. We'll end up with a piecewise function for each internal load. Okay, so for example, a T value that depends on where you are along the beam, that's equal to, well, in this case, there's not going to be any T in the example I'm giving. Let's see. Let me do the one that we would have here. So like V of X would be negative 500 for X values between 0 and 0.5, and positive 500 for X values between 0.5 and 1. Okay, so that's what we're trying to do. Where are the breaks in these piecewise functions? So to do this, you have to identify the places where these subfunctions can change. You know that negative 500 there is a subfunction, the positive 500 is a subfunction. So we have to find the places where the subfunctions can change. And so those are first, endpoints. Well, that's pretty obvious. Second is the locations of all point loads. locations of any point on, bless you. And the third and the last one is places where any distributed load changes. Places where, I guess, let's say the distributed load function changes. Okay, so what I'm going to do this same super simple example, this one, and the only places where the subfunctions can change on this are the two endpoints and the 1,000, okay? Nothing else is going on that's in that list. So we're going to have one subfunction that represents all x values from 0 to 0.5, and another one that represents all x values from 0.5 to 1. Okay. This is like the 5th example in a row that I'm doing with this same stupid beam. But you can do this with other beams too. Okay, so 500 down on each end and 1,000 up in the middle. So where can the subfunctions change? They can change at x equals 0, x equals 0.5, and x equals 1, like if we're working from left to right, okay? And so that means that our cuts, our free body diagrams are going to fall in those ranges, which means we're going to do 2 cuts. I'm going to call this, so n is equal to 3. There are 3 places where this subfunction can change. And so we're going to have to do 2 cuts, which is n minus 1, you know. Okay, so cut 1. We're going to use x as the length of the beam that we're isolating, of the piece we're isolating. And for cut 1, what can our x value be? It can't be 0, but it can be anything. It can be 0.000001. And it can't be 0.5, but it can be 0.499999, right? So x can be anything between 0 and 0.5, not including the endpoints. So x is in the range from 0 to 0.5, not inclusive. And that free body diagram, I'm just drawing one free body diagram that represents all these. There's a 500 here. We haven't gotten to the 1,000. And then there's T, V, and M. And this length is X. And I'm going to use this as my about point. Any questions about that? Okay, so Newton's second law says 0, negative 500 plus T0 plus 0, negative V is equal to zeros. So we get that T is equal to 0, and we get that V is equal to negative 500. And now the moment equation, the 500 doesn't produce a moment around that about point because it's through the about point. But we have to add on the couple, M. And then V is going to produce a moment. And its moment arm is X. So we're going to have a Vx. And now we have to think about, would that make it rotate clockwise or counterclockwise around that about point? That force V, the way I have it drawn. Clockwise, so this is negative. And remember, you could always do this by writing out the table and just doing it as a rigid body. Okay, so this is equal to 0. Plug in negative 500 for V, and you get that M is equal to Vx, so negative 500x. Are you with me on that? So what we did by taking all of the possible cuts that are qualitatively similar, representing the length by x, we came up with these functions that represent the internal loads over that whole length. So these functions are valid for any x's between 0 and 0.5. Okay, so now we have to go to cut 2 and do the same thing. Well, this has to represent all the places that the right end could fall from just after 0.5 to just before 1. Okay, so x's for this cut are anything between 0.5 and 1, not including those endpoints. And this free body diagram generally is going to, no matter what x value you chose, it's going to have the 500 Newton force on the left. It's going to have the 1,000 Newton force up a distance of 0.5 from the left. And then it's going to have the internal loads T, V, and M. And as far as distances, this distance is 0.5. And this distance is x. Any questions about this free body diagram? And about point on these, just always make the left end your about point. Okay, so Newton's second law says 0, negative 500, plus 0, positive 1,000, plus T0, plus 0, negative V is equal to zeros. So T is 0. V is positive 500. Remember, it was negative 500 on the first part. Now it's positive 500. And the moment equation, the 500 doesn't produce a moment. The 1,000 has a moment arm of 0.5. And would that produce a clockwise or counterclockwise moment with that about point? counterclockwise, so this is positive. Then we have m. We have the minus Vx that always appears because that V is always going to make it rotate clockwise. And this is equal to 0. And so solve for m, and you get that m is equal to 500x when you plug in the V value that we already solved for, because m is equal to Vx minus 500. So that. And so what we got overall is for this whole beam where x equals 0 represents the left end and x equals 1 represents the right end. T of x is 0 everywhere. That's not too interesting. V of x is a piecewise function that's negative 500 for x between 0 and 0.5 and positive 500 for x between 0.5 and 1. And then m, this is the only one that really looks like a function, is negative 500x for x between 0 and 0.5 and positive 500x minus 500 for x between 0.5 and 1. And if you want to see what these look like, you can think of plotting these as functions. So there's 0.5, there's 1, this is, the x-axis is x, this is t. Well, t is just 0 the whole way. V so there's negative 500 newtons, there's positive 500 newtons, and we got this and this, and then people connect them like this. That makes you look like an insane person, but that's what everyone does. So that's not a function if you draw it like that. But what would really happen, by the way, is there's no such thing as a point force. There's only distributed loads distributed over very small distances or areas. And so this would really, be slanted somewhat or curved somewhat or whatever. So it doesn't tell us much about what's going on right at that point. But away from that point force, you can trust those values. And then the last one, the bending moment. We started on the first part with negative 500x. So if you plug 0.5 into, plug 0 into negative 500x, you know that you get 0, so it starts there. Plug 0.5 into negative 500x and you get negative 250 Newton meters. Plug 0.5x into the right function and you 0.5. So you get negative 250 again, which, so that just means that this function is going to continue from the same spot. So you get a line like that, and then a line like that. Okay, so without knowing anything about, I mean, like if you're really doing this analysis of like whether you're afraid this beam's going to break or whatever, you use the materials you have, you do stress and strain analysis. But even without that stuff you do in B form, but even without doing any of that stuff, you can look at this and say, if I'm looking for where I'm most concerned about this breaking, where would it be? The tension isn't causing any problems. There's no tension anywhere. The shear force is basically the same magnitude over the whole thing. So, except for whatever's happening right at that point load. But the bending moment, you can see very clearly the magnitude goes up as you get toward that, from either side as you get toward that point force. And so based on this, you would say, I'm most concerned about this thing breaking as you approach that point force from either the left or the right at the center. Okay. And so that's what this internal load calculation can tell you. It can give you a sense of where you're concerned about fracture or deformation. And this explains why, I've basically been using, so when I started talking about internal loads, I drew the picture of the thumbs and the breaking the stick, the hands breaking the stick. From looking at the external loads, there's nothing to show you why it's going to break between the two thumbs. But an analysis like this is what would tell you that's going to break in between the two thumbs.
The reason about the bridge.
No, that bridge apparently collapsed just because of the way they did the joints. They just did a calculation wrong, and the joints are on those bridges. They do the calculations like the joints are all ball and socket joints, or else or pin joints if it's 2 dimensions. But it's not really that. It's they take these big, thick steel plates and screw the beams into the big plates. Those are called gusset plates. And they made the gusset plates too thin, and just eventually, after many decades, it buckled, and that was that. Yeah. The 35W bridge that collapsed in probably 2008. Yeah.
What about the one that kept like moving?
Yeah, that one's cool. That has nothing to do with this, but that one's funner to watch. Yeah, what's that one? The Tacoma Swallows Bridge or something? That's funny. Yeah. The problem with that was that the frequency of the forcing that was produced by the wind was like applying like a periodic forcing to this thing, and the frequency of that forcing matched the resonant frequency of the bridge, and so it just got bigger and bigger and bigger until it just blew apart. Yeah, so that's a dynamics thing, not a statics thing. But the 35W bridge, that was just a statics miscalculation. Yeah, right. Well, you do those calculations like the thing's a truss, but instead of actually making pin joints and ball and socket joints, they just attach everything to these big gusset plates. And you can calculate what the loads are going to be on those gusset plates, and then you make them as thick as you need them to be to support those loads. And they miscalculated and made them too thin, and so they buckled. Yep, but it was just a truss calculation was all that you need for that. Any questions about this? Okay, so now let's do an example where it starts out like a rigid body statics problem, and then we'll go into this. So let's say that you have a pin joint on the left and a roller in the middle. And then at the end, you have a 500 Newton force to the right and a 1,000 Newton force down. And we want to calculate the internal loads. This thing has a length of 2 meters. So it's 1 meter to there and 1 meter to here. Okay, what about the weight? What about the weight on the last example that I kept doing and doing and doing? I mean, we haven't done any problems in this whole class, basically. I guess we've done a couple 3D ones with no weight, but for the most part, we always include weight. But in my one example that I did 5 times in a row, there was no weight. Why was that? And why is there no weight on this? Because of my inherent laziness? That's not why, although I can't deny that. That is why it would be a reasonable thing to do, but that's not why either. The reason is that with what I've done with internal loads so far, we can't deal with the weight yet. Because remember that weight is, even though we treat it like a point force at the center, it's really a distributed load, okay? And so before we can do this, we'll have to deal with, how do we treat distributed loads? So that's the next thing we'll do. And then we'll be able to include weight and everything. Okay, so the first thing we need is the external loads. So free body diagram of the whole thing. We have a pin joint at the left. I'll call that RA. We have, I'll call this RB, a force from the roller at the middle. And then we have the 2 applied forces, the 500 and the 1,000. And I'll use the about point at A again. And you could write out a table for this and everything, but again, this is just a horizontal, everything's happening in a horizontal line, so it's just easier to do it the way that I did it in the last example. So what do we have? RAX, RAY plus 0 RB plus, you can treat this as a vector. So 500, negative 1,000. And so we know that RAX is negative 500. And then the moment equation, that force RA doesn't produce a moment. The force RB has a moment arm of 1. And would that be a clockwise or counterclockwise rotation? Counterclockwise, so that's positive. The 500 doesn't produce a moment because its line of action goes through the pin, but the 1,000 has a moment arm of 2. And would that cause a clockwise or counterclockwise rotation? Clockwise, yep. And so RB is equal to 2,000. And so RA is, or RAY is negative 1,000. Okay, so now this looks like if we plug these values back into the free body diagram, we have RAX this way at 500, RAY this way at 1,000. The roller force, RB, is up at 2,000. And then on the right end, we have the 500 and the 1,000. Okay, so where are the subfunctions going to change? Or what are the candidates for them changing? There's no distributed load, so the distributed load functions don't change, but they're the two endpoints. And then there's one place that's not at the endpoint that has a point load, and so you have to include that one too. So n is equal to 3, so how many cuts are we going to have to do? 2, yep. Okay, so cut 1 is going to be for x values between 0 and 1. The free body diagram, we have the 500 to the left, we have the 1,000 down, but we haven't made it to the 2,000 up, so all we have besides those on the left are the internal loads. And this distance is x. And this is the about point. It's recording, yeah. Okay, so Newton's second law says I'm going to lump the two forces that are at the same point here into a single vector. So negative 500, negative 1,000. Plus, you can also lump the t and negative v into one vector. They're at the same point. So t is equal to positive 500, v is equal to negative 1,000. And now the moment equation, the 500 and 1,000 don't produce any moments. So all we have are m minus vx is equal to 0. And so m is equal to vx, which is negative 1,000x. Any questions about that cut? And now we go to the second cut, where x values are between 1 and 2. And we always go all the way from the left up to our cut point on the right. So we still have the 500 and the 1,000 on the left. Now we also have the 2,000 up. And then T, V, and M. The distances. This distance is 1 meter. And this distance is x. Remember, x is between 1 and 2, so whatever x is, it's bigger than 1 meter. And our about point is here, like always. Okay, so Newton's second law says negative 500, negative 1,000, plus 0, 2,000, plus T negative V is equal to zeros. So T is 500 and V is positive 1,000. And then the moment equation, there's no moment from the 500 and 1,000. From the 2,000, there's a moment arm of 1. And is that clockwise or counterclockwise? Counter, so that's positive. And then there's plus the couple m minus Vx is equal to 0. And so m is equal to Vx minus 2,000. So 1,000x minus 2,000. These first ones were valid for x on 0 to the interval 0 to 1. The second set is valid for x's on the interval from 1 to 2. You could write that out in piecewise function notation. I think it's usually more helpful just to get an idea of what the graphs look like. So, okay, what do these look like? So for t, it's positive 500 on the first half, positive 500 on the second half. Since that T is positive, does that mean that this thing's in tension or compression? Tension, yep. Positive always means tension, negative always means compression. And then for the shear force, We have negative 1,000 and then positive 1,000. So this on the first half, this on the second half, connect them like a crazy person. And then the last one is the bending moment. So this one starts out negative 1,000x. It's going to look sort of the same as it did in the last example. It's going to go down to 1,000. It's going to go down to negative 1,000 and then back up to 0. So this will look like this. Remember, that's in Newton meters. Any questions about that? Want to know a weird coincidence? This is crazy. Watch this. What's the slope of m with respect to x here? It drops 1,000 over a distance of 1 on that first half, right? So negative 1,000 is the slope on the first half. Positive 1,000 is the slope on the second half. Look at V, negative 1,000, positive 1,000. Look at the last example. The slope, dm dx, is negative 500 and then positive 500. Negative 500, positive 500. It's always like that, and we'll talk about that later on in a little more like context and stuff. But yes, you can always check your work. dm dx is always equal to v. Okay, so that's it for today. I'll give you a couple examples like this with point loads. And then on Wednesday, we'll start talking about using distributed loads. And then the biggest part of that is then we can include weight on these members.